Hello everyone, I Nikhil welcome you to Vigyan Bharat. In this lecture today, we're going to discuss the problem of the day for 7th of September, and today we're going to discuss the topic of Bernoullis equation, what we mean when a differential equation is said to be Bernoulli, that we're going to look, and after that I'll going to give you a partial proof of how you can prove it to find its general solution, and based on that I will give you around 5 problems which you have to try and solve. So let's begin our lecture. Let's see. We say an equation of the form, just try to see here what I have marked by equation 1. An equation of the form dy by dx plus px into y equals to qx times y to the power n, where of course this n cannot be equal to 0 or 1. Okay, so such a differential equation is said to be a Bernoullis differential equation. Now try to see here something, that this p and this q, this p as well as this q, these both are functions of x, that is they are function in the variable x. They may be constant also, so some, say for example, px may be x square, px may be exponential of x, px may be log x, anything, any function of x, similarly qx, and they may be constant also, px equal to 1, px equal to minus 1, half, like that. Okay, and here try to observe that this n cannot be equal to 0 or 1. Why? I ask you, try to think why I have restricted my n to be not equal to 0 or 1. I just give you a hint and you try to answer me in the comment box, that if we choose n to be 0, then here this exponent will vanish, this y to the power n will not be there. Then you will be able to find that equation 1 reduces to some different form, different type of differential equation, maybe a linear differential equation or an exact differential equation. So try to answer me after verifying why this n cannot be equal to 0 or 1. If we choose our n to be 0 or 1, then it will reduce to some other types of differential equation. That's why we have restricted it to have a different form. Okay, so such an equation is said to be a Bernoullis differential equation. Here this Bernoulli is the name of a mathematician. So let's move forward. Let's try to see how we can obtain its general solution. In order to obtain its general solution, I assume that you know how to solve a linear differential equation that I expect from you. So it's pretty easy now. In order to solve equation 1, we multiply, first this is the first operation we do, but we multiply both the sides of an equation 1 by y to the power minus n. Of course y is a non-zero quantity and n is some positive integer, so you multiply it and then you move forward. After doing some calculations and simplifying, we reach to the equation 2. Now in order to solve such an equation, I have to do some operation. So what I did here, I did a substitution, and this is that substitution. I chose this expression, the coefficient of p, y to the power 1 minus n equals to v. So I assume it and I differentiated it with respect to x. You can easily do that using some, you know how to do differentiation. And after, when you will differentiate this quantity in equation 2, this thing can be written in terms of v here, like this, in terms of dv by dx. You can substitute that, and again I have written here that this expression makes sense as n equal to minus, n cannot be equal to 1 because that we have already assumed in the given when we were defining the Bernoullis equation. So if you substitute all these values, then equation 2 reduces to this equation. And further, you multiply both the sides by this non-zero quantity 1 by this factor, obviously 1 minus n. If you multiply it on the both the sides, then this will result in this third equation. And now it is a very simple, I would say, linear differential equation in v and x, which you can easily solve by first calculating its integrating factor, and then the general solution will look like this: v times integrating factor equals integral of the right hand side, whatever it is, you call it some new, say r times v times integrating factor equals to integral q times, that is r times integrating factor times the variable of integration dx. To solve this, and you will find the answer in terms of v, and replace again v by whatever the substitution which we have made above. If you remember, we assume that y1 minus n equals to v. So you can replace this value and you can easily find a general solution. I have just here given a hint how we calculate in general the integrating factor, and then I left it to you. So try to find its general solution. So now here today I have these 5, I would say, very good problems, 5 very good interesting problems based on Bernoullis differential equation. So try to solve each of them. The one which I have marked by star, these are some good problems. When you will solve them, you will maybe you can stuck somewhere. So try to solve each and every of them, each one of them. And I just say again that this fourth problem is a good problem. Initially it is of some different form. You can reduce it to form a Bernoullis differential equation of that type. Try to solve it. Here this phi is a function of x, and in problem number 5 again it's you have to reduce it, and you have to find the curve which passes through this point. That is, if suppose our curve is this y, and it is, we know, is a function of x, then if it satisfies this condition, this says that y of 0 equals to pi by 4. It means this basically, when this is your x, then this curve assumes this value pi by 4. So you have to solve using, at the end, you have to use this condition in order to calculate the arbitrary constant. Okay, so these are 5 good problems. Try to solve each and every one of them, and if you find like any difficulty anywhere, you can drop me in the Telegram group, whose link you can find in the description of this video, as well as in the about section of our channel. And if you like the video, then do give us a like, and feel free to reach out to us if you have any queries anywhere. And thank you so much for watching. We'll be moving ahead with another interesting video. So thank you so much.